Welcome to Brain Vision.
We know that the magnetic force is given by I times L cross B, but that's the case where the magnetic field is uniform. For a case where magnetic field varies with the length, the change in force can be written as I times dl cross product with magnetic field, and this is the equation that we are going to use, and we are going to apply this equation to each side of the loop. Now for each side of the loop, dl is parallel to that side of the loop and is in the direction of I. Since the loop is in the xy plane, so z is 0 at the loop and by is 0 at the loop, because uh, by is basically, we just plug z equal to 0 in this equation. Then b vector will be equal to p0y over L times k cap, because this just got 0 here. Now we are going to apply this and into this equation, and we are going to do the first part now. So for the first part, the magnetic field lines in the z plane are to be sketched. So let's do that. So let's say this is the x and this is the y-axis, and magnetic field is along the positive k-axis, and it varies with y. So there is no need for the x-axis to be here. So we are gonna use y and z axis, because those are the only components contributing to the magnetic field here. Z is the direction and y is the distance with which the magnitude of magnetic field changes. And we see that uh, the magnetic field B is varies linearly with y. That means this is going to be like this. And for y, for the origin. Now if the y changes, this is how it's going to look. Yeah. So that is part A. Now for part B, we have to find the force. So let's find it for side 1. Let's mark the side first. So this is side 1. L2 is let's call this to be side 1. This to be side 2. This to be side 3, and this to be side 4. And for side 1, let's call the force to be F1. So this is given by this equation over here. So basically integral over this equation. So I times dl times b sine phi, and the integral over that. But sine phi is basically 1 because phi is 90 degree, as the magnetic field is perpendicular to the segment here. Basically magnetic field is perpendicular to the plane of the whole system. So for every case, this force is going to be 0. sorry, this angle is going to be 90 degree. So this gives, so I is a constant, so it comes out, and B naught is a constant, L is also a constant, so they come out as well. And we have Y, and DL is basically the change in length along this direction. So DL is going to be equal to dy because this segment is along the y-axis, and the integration goes from 0 to L. And by right hand rule, so let's do that later. First, let's find the force. F1 is equal to half times V naught over L times I, and we apply the right hand rule, so that gives the force towards right or towards the positive x-axis. So this is the force for the first segment. And for those who don't know what this integration is, so I'm just going to write it over here. So let's call this y to the power n, where n is some integer other than -1. So if this goes from a to b, so the integration of this is basically y to the power n plus 1 over n plus 1, and you apply the limits from a to b. This gives b to the power n plus 1 minus a to the power n plus 1 over n plus 1. And that's what I did over here. And if n is -1, the integration is just going to be the logarithm of y, and then you have to apply the limits here. So now we do the same for f2. So f2 is equal to integration over I dl. B sine phi is 1, and the limits are L to L. Now since the limits are same, we don't need to explicitly calculate this integral. This is, okay, so is this value, oh sorry, okay, so dl, we have to see what the dl is. So dl is basically x here, because dl is parallel to the x-axis. So our limits are going to be the limits of x and not the limits of y. So that's going to be 0 to L, and I is a constant, B naught is a constant, also L. These are the limits of dl, and dl is basically dx as I said there, and we have a y from the magnetic field, and we find this value to be I times B naught over L. So the value of y is basically a constant here and is equal to L, so that comes out, and we just have to integrate over dx now. And this gives the value to be I times B naught times L, and the direction is given by right hand rule being applied to the direction of current and magnetic field, and we see that this direction is going to be towards negative y direction. So our force is going to be this. Now we do the same thing for F3. So for F3 we have I dl b sine phi is 1, and so the constants come out of the integral, and we have a y from the magnetic field, and we have to see what dl is. So for the third segment here, dl is basically negative y again. Sorry, dl is basically dy again. So we do that and we see this to be equal to IB naught L over 2. This is basically same in magnitude to what we found here. And let's find the direction now. So we apply right hand rule and we get the direction to be along. Okay, so one thing to note is dl is actually negative y, negative dy, because this is going towards the negative y-axis. So dl is going to be negative of dy. So this is basically negative. And the direction, if you apply the right hand rule, you'll see that the direction is, so I is k cap, j cap, and b is k cap. So j cap cross k cap is basically I cap. We can also not include the negative sign and do the cross product as negative j cap cross product with positive k cap, and you'll get the same answer. So for the last part, we have, I forgot to write the limit, so this is just L over 0, and let's make this plus, and we arrive at this result. So I think this is simpler than what I was doing earlier. Yeah, just take the limits as the current flows, so L to 0, and take dl to be equal to dy. Now we find F4, so that is I times dl times b again, and the constants come out of the equation, and we have a y from the magnetic field, and dl is dx again, and we have the limits from L to 0. So yeah, this is simple. Now we get the value to be IB naught over L, and in this case you'll see that y is 0. So for this segment, the fourth segment, that means that the integral is 0, and this gives the force to be 0. Next, the net force is going to be a vector sum of all the forces. So that gives F1, the net F net, to be equal to F1 vector plus F2. Let's do it in the next page. So F net is equal to F1 plus F2 plus F3 plus F4. This is basically 0 as we calculated, and F1 and F3 have the same magnitude here, and F3 which I calculated here, but they are opposite in direction, so they add up to 0, and we are just left with F2, which is negative of I times B naught times L j cap. So this is the net force.